today we're going to talk about how to do multiple regression and correlation using R. And this is going to make a lot of the things that you guys were doing on the homework much simpler and easier. So you guys hopefully already have the data. Is there anyone that doesn't have the data loaded up yet? Okay. So if we have the data, what is the deal on this? I don't know. Sorry, it's all. Anyway, today we're going to create our own data frame because the original data frame has more information than we want in it. So it has stuff, homework 1 scores, homework 2 scores, up to like homework 20-something scores. And we don't all want that right now for some of our analyses. So let's just get what we want. For now, it's just going to be the test scores. So we want test 1 and test 2 scores. So you can create your own data frame. You want to name it something so you have access to it later. You can name it whatever you want. If you want to just be able to type in the commands that are up here, I would name it myDF, the F for data frame, and then just say data frame. And then you can name the variables whatever you want, and you tell it what you want inside of it. So we want data T1. So this is the test 1 scores in that original data frame that you loaded up. And these are the test 2 scores from the original data frame that you loaded up. I used the different variable names here to show you guys that you can name them what you want. Name them whatever makes sense for you. Yes?
There is a parenthesis on the end of the my test.
This?
Yeah.
Yes. So data frame, just like the other functions, we would say correlate the stuff that's in here. Or do an ANOVA with the stuff that's in here. We're saying make a data frame out of the stuff that's in there. If you attach the data, originally, you could have also just said myDF equals data frame, my test 1 equals T1, my test 2 equals T2. So you can work with the data however you're most comfortable. You good?
Do you know attached data?
No, I don't think at this point. But if you had written attached data, if you'd already had that attached, then you don't need to say get T1 out of this data frame because the data are already there and available. So you could just say this is going to be equal T1. Okay?
Yep.
All right, so what's in our data frame? Do a stir in myDF. Test 1 and test 2, that's it. So if you did a stir on data, you're going to have, we'll say like 32 observations or 43 observations for 32 variables. Now it should say something like you have 43 observations for 2 variables, right? So you should have something like this. So this is what we're going to work with. And the reason that we made a new data frame is because it's going to allow us to do some things really, really easily. Okay, so this has only what we want. Now let's correlate the test scores. So core myDF, my test 1. So we're going to correlate the test 1 scores in your data frame named myDF with the test 2 scores in your data frame. You should get 0.67 stuff. What if you had attached myDF? If you said attach myDF, what could you have done differently? Yeah, you could have just said core my test 1, my test 2. All right, perfect. So let's do this a bit differently. So this is how we've been doing it, right? We say correlate this variable with that variable. Now, all of the variables that we're interested in correlating are in the data frame. So you can actually just do this. Core myDF. And what do you get? It's not going to be 0.67. It'll be something else. 1 and 0.6 looks something like this, right? This is called a correlation matrix. And what the correlation matrix contains are correlations between each variable with each variable. So here we have a correlation between test 1 scores and test 1 scores. The correlation between something and itself should always be what?
1.
Should always be 1. The correlation between test 2 scores and test 2 scores is also 1, right? Now the correlation that we were interested in was this one, right? The correlation between test 1 scores and test 2 scores, this is 0.67. So we know that there's a linear relationship. Well, we haven't run the statistics yet. But if this is significant, this means that there is a linear relationship between test 1 and test 2 scores, right? So the variables correlate perfectly with themselves. And notice that these two things are the same. I think for one of the homeworks I may have said something like correlate test 1 with test 2, and now correlate test 2 with test 1. You get the same thing. Because the relationship between the two is the same regardless of whether you look at one first or the other first. So it's basically redundant information. So when we say something like this, correlate, and we give it a data frame, it's correlating all of the combinations of the pairs of the variables that are in that data frame. So in a situation where you're just correlating two variables, it can be really easy to just say something like this, correlate the two. But if you have 18, 20 variables, you might not want to have to do that 18 or 20 times. So instead you can give a data frame that has all those variables in it and get all those correlations automatically. Now, lots of times if you are reading journal articles, you will not always see the entire matrix filled in. Some of the information may be missing. And I say missing because it's not really missing. So what is sort of missing here?
Correlation between test 1.
This is what's missing here, right? But it's not really missing. Why isn't it really missing?
Same.
It's here. It's right here. It's the same thing. So by only showing part of the matrix, if you understand what the matrix is, you can easily fill in the missing values yourself, and you save ink. Yay! It's an earth-friendly way to present data. And it's also a little less cluttered visually, especially when you have a lot of correlations. Okay. So we have ones on, not on the diagonals, on this diagonal. On this diagonal we have the ones. We'll see a more extreme example of missing data a little bit later. Oh shoot. In addition to finding correlation matrices, we can also find covariance matrices. So go ahead and do covariance, MyDF, and what do we find? Should get this, right? So what do we have? Well, it says that we have the variances on this diagonal, right? So the variances are on this diagonal. So this is the variance for our test 1 scores. This is the variance for what? Our test 2 scores. And what are these?
The variance between my test 1 and test 2.
Yeah, it's the covariance between test 1 and test 2. So those are the covariances, and on that other diagonal we have just the variances. So if you have a homework question and it's asking you to find covariances, you can just covary the data frame and get those things very, very quickly. Okay. Like correlation matrices, often half of the covariances are missing because, again, it's the same regardless of whether you put in one first or the other. Okay, so this is the way we tested correlations before. Don't do this. You guys have done this, at least those of you who have done the homework have done this already, right? You figure out the number of pairs that you have, you figure out the correlation, then you can figure out the t-score based on the correlation and the p-value based on the t-score for the appropriate degrees of freedom. We're going to do this differently now. So we're going to do core.test. Have any of you figured this out?
T-test?
Not core. t-test, but core dot test. But maybe some of you would jump on the internet and Google things to find out how you can do this. So what are we saying? Okay, we're saying we want to test the correlation between our test 1 scores and our test 2 scores. What'd you say?
It's perfect.
It's perfect. Wow, not many things in the world are perfect, but this is pretty nice. So it gives you a lot of information. A lot of information. What does it tell you? It gives you the correlation, right? This is the thing that we found earlier. So it gives us the correlation. What else does it give us? It gives us the value of t that we would have for that correlation. It gives us the p-value. It tells us what the degrees of freedom are so we don't have to calculate them ourselves. It also gives us a 95% confidence interval by default. That's kind of cool. That's sort of like the function t-dot test. T-dot test told you what the t was, it told you the p-value, told you what the degrees of freedom were. It also gave you a confidence interval. Woo! Sweet. Okay, so core test. Like t-test, you can give it different parameters. So we can perform different types of correlations. I've sort of hinted that there are different types of correlations. The correlations that we've been working with have been Pearson correlations. There are others. I'm not sure whether or not we're going to talk about the others. We may not. We can also have different hypotheses, right? So previously we've talked about just the hypothesis that it is equal to. But we could do a hypothesis that it is less than or equal to, or greater than or equal to. So we can have our different hypotheses about the correlation for those variables in the population. We can also calculate different confidence intervals. So if we had a hypothesis like this, our population correlation coefficient is greater than or equal to 0. We want to use an alpha level of 0.01. Alternative equals less. What else? Conf level equals 0.99. You guys are brilliant. There we go. So go ahead and do it. Make sure you get the same answer.
Yeah. P-value is 1.
Well, it's not 1. But within the rounding error, I mean, if we went out far enough, it would not be 1. Right? It would be 0.999999999999999 something. But it's close enough to 1. It's 1. And 99% confidence interval, what does that range from? So, there it is. What does it range from? A perfect negative correlation. Correlations only vary between -1 and 1. So we shouldn't see anything less than -1 or greater than +1, right? Now, remember when we were doing t-tests? And if you told it the confidence level with the alternative, it would give you the confidence level that matches up to like that hypothesis. However, we often didn't want the confidence interval for that. We wanted, what type of a confidence interval? We wanted the smallest confidence interval. So is there anything that we could do to get the smallest confidence interval?
It was 210 if you want to give.
Yeah, if we wanted the smallest confidence interval, we got rid of this alternative, right? Which didn't give us the right values for our t-tests. But they did give us the smallest confidence interval around that. So if we wanted the smallest 99% confidence interval, just get rid of that alternative, or specify 2 dot-sided, and you should get this. Right? And now you have the smallest confidence interval around the observed correlation.
I think that we could have had an alpha of 0.002 1, but you don't have to get the 99% coverage.
So you're saying like you could use an alpha of 0.01 but then calculate a 95% confidence? Yeah, you could. You could. Typically, if you are using a particular alpha, you might create a confidence interval that covers the same percent, right? But you could. In fact, in most journal articles, you will often, if you are reporting confidence intervals, you will report a 95% confidence interval, even though you may have had something that was significant beyond an alpha of 0.01 or even 0.001. Okay, so simple linear regression. We started with the correlation, and then we used the correlation to do a regression, which is basically to find a line that best fit the data. The correlation by itself told us like the direction and the strength of the relationship, but it didn't give us like values that we could use to predict things if we were interested in making predictions. So we've talked about finding regression coefficients and constants. We didn't talk about testing them. We only talked about testing R, the correlation coefficient, right? You can test the regression coefficients and constants. Now, the cool thing is that the tests for the coefficients, the coefficients are they the slopes or the intercepts? The regression coefficients. The coefficients are the slopes. So, for the coefficients and the corresponding correlation, the tests that you get are going to be exactly the same. You will find the same p-values that you did. For the constant, it's going to be a bit different. I'm not going to teach you how to do these tests the long way. You guys have already learned a lot more than a lot of undergraduate students taking an intro to stats class have by learning how to compute the t-test for the correlation the long way. So I'm going to go easy on you for this. So the old way that we found the coefficients and we found the constant was this, right? So the coefficient or the slope was just the correlation times the estimated standard deviations. And then the regression constant or the intercept, this was just the mean of y minus the slope times the mean of x, right? And this is what we found in the previous class. We found a slope of 0.69 and a constant of 17.4. Let's do it the new way. So, remember when we were doing ANOVAs? We were creating models. We were creating models that said, okay, our dependent variable is basically a function of these other things. For our linear regression, we're doing the same thing. In creating that y equals mx plus b type formula, we are modeling a relationship, right? We're saying that the data are modeled by these two things. Some slope, or slopes if we have a multiple regression, and some constant. So our model, basically, we have a model of test 2 as a function, as estimated, as predicted by test 1. Okay? So we've got test 2 is predicted by test 1. Now, instead of using AOV, we're going to use LM. LM stands for, can anyone guess it? Linear model. That's right. Okay. So once we have our model specified, we can say, okay, we're using this linear model. This model that we have is a linear model. And we don't have to do it this way. We could just specify everything originally. And remember when we were doing AOV, we specified the model, and then we said where we could get that data from? So here we told it where you get it from and what the data are together. But just like with the ANOVA, we could do it the other way. So we have some model of test 2 as a function of test 1, and these scores are in the data frame. Okay, so if you do myLM, type in myLM, what do you see?
Coefficient.
Oh man, it's running off. You see, Coefficients. An intercept. So this, what is this? It should be, that's 17.4. That is the intercept, it says, intercept. And this other thing, 0.6,
Slope.
that's a slope, right? Cool. So we have the slope and we have the intercept, and Ellen can tell this to us automatically by specifying the right mark. So that's kind of nice. Now try this. Ooh, yay. So you got something like this? You got a lot of information, right? A lot of information. Whoa. So what do we have? Everything. Not everything. It hasn't told us semi-partials. It hasn't told us the partials. But it has told us a lot. So let's take a look. So this is just the formula that we said. This is the model that we are trying to estimate test 2 from. And what do we see? This first thing is residuals. We've talked about residuals before. This is the error. This is what is left over after you make your predictions about test 2 from test 1. And it also gives you a breakdown of the errors. So I'm not sure if I mentioned this before, but the linear correlation is based on the assumption that the variables are normally distributed, and also that the errors are normally distributed. So we haven't talked about that. Well, we did now. So just like the t-tests and the ANOVAs, right, we made these assumptions that the variables were normally distributed. If we didn't make that assumption, we needed to have a sample size great enough. Regression and correlation are similar. Okay, so we have the residuals, and we get an idea about what the minimum and the median are, and if we were to plot the residuals, we could plot the residuals and see what they look like. Okay, we have our coefficients. One of the coefficients is not really the coefficient in the way I described it, it's the constant. That is the
Slope. Intercept.
The intercept, that's this. That's 17.4, that's what we just got. And what else do we see? We see the error. And we see the t-value. And we see a p-value. Right? Now, notice it says PR. PR. Huh? PR. Where have we seen PR? Not 2 keys. We have R, a correlation coefficient. We have SR, a semi-partial correlation coefficient. And we have PR, a partial correlation coefficient. The standard linear regression model is using the partial correlation coefficient to create these, to create the slopes, right? So that is the partial regression coefficient. And we see that it is highly significant. The p-value is way, way less than 0.05 if we were using the traditional alpha level. So if we were using the traditional alpha level, what could we say? Reject the null. The null, if it was that the population correlation was 0, we say that there is a correlation between our test 1 and our test 2 scores. Okay. So we have errors, we have our regression constant, we have our regression coefficients, we have the t-scores associated with them and the p-values associated with them. We also have some other things down here. This multiple r squared, that's the coefficient of determination. That is how much variance in our test 2 scores is explained by the linear relationship between our test 1 scores. And we also have this other thing, adjusted r squared. What is adjusted r squared? We haven't talked about this. No, it's not the uniquely explained.
Not explained?
The uniquely explained is like this.
It's not explained.
So when we talked about standard deviations and variances originally, we had like a biased version and also an unbiased version.
Unbiased?
Well, it turns out that our multiple r squared is slightly biased, especially for small sample sizes. So, I mean, imagine if you had some population and there really was no correlation at all in the population considered as a whole. If you took two observations, right? Any 2 points make a line. And you don't have enough degrees of freedom to test for 2 points, but for 3, you would. So imagine you have a line, and odds are that that third thing that you take isn't going to perfectly balance things out to give you a correlation of 0. So just like we're almost never going to observe someone that is at the mean height or at the mean weight. We're almost never going to observe a correlation of 0, even if the correlation really is 0 in the population. So this adjusted r squared takes care of that. I'm not going to teach you how to calculate that because it's way beyond the scope of this class. But if I ask you what the adjusted r squared is, you have it. All right. Let's create a new data frame. So what we just did, that was a simple regression, a simple linear regression, where we're just trying to predict one thing from one other thing. But lots of real-world situations involve multiple variables, right? So let's make a new data frame that has multiple variables. Do this. New df equals data, comma, 28.30. Now these are brackets, not parentheses. So what we are doing here is we are getting all of the data. There's nothing before this comma here, but R assumes, okay, there's a comma. We want all of the data for the 28th, 29th, and 30th variables that are in the data frame named data. If you did a stir data, you see that there are 43 observations of 32 variables. And if you look down, the 28th, 29th, and 30th are test 1, test 2, and our homework average. What you've been working with on the homework. Okay, so if you do stir new df, what do you get?
T1, T2, and homework.
You have T1, T2, and the homework average. So 43 observations of 3 variables. So you can create data frames in different ways. Okay. So, I'm probably on the homework not going to tell you to just make a new data frame on your own. If I'm doing that, I will give you the code. But this is, for those of you who are interested in participating in people's labs or running your own statistics, this can be a useful thing to do. Okay, so let's do the correlation matrix for our new data frame.
We have 9 different correlations.
We have 9 different correlations, right? We have a bunch of 1s. What are the 1s?
Correlating itself.
Yeah, the correlation between test 1 and itself is 1. Duh. The correlation between test 2 and test 2, it's 1. It has to be. So we have 1s on this diagonal, just like we did before. And the stuff that we're really interested in is here and here. Right? So the correlation between T1 and T2, 0.67. The correlation between T1 and homework average is 0.54. And the correlation between test 2 and our homework average is 0.64. Now, if you wanted to test these correlations, you'd have to go through this individually. So do a core test, new df, $T2, with new df $ homework average. You could do that, but that's not really a great idea. You'd be running multiple correlation tests. And if you have a 0.05 alpha rate for each of the tests, what happens by doing multiple ones is you actually increase the probability that you make an alpha error above the 0.05 rate that you want. So typically we're not going to do this. Okay, so here's a matrix with even more missing data. What do we have here? So notice that this is this. The correlation between T1, test 1 and test 2, correlation between test 1 and test 2. This is that, this is that. What else has been eliminated? We've gotten rid of all of the ones, the correlations between the variables and themselves, right? Well, I guess not all of the ones. We could have the one there, right? But that's a lot of information that we already know, that we don't need to see because we know what it is. So we are basically showing the correlations that we're interested in, and we're ignoring the other stuff. All right. Let's do the multiple regression now. Let's attach the data now to see how we would do it with the data being attached. So attach new df. All right, now let's combine the previous steps into one statement. So previously we did something where we said there's some model and we have LM, model, and then we said summary. We said this was my LM, I think, and then my LM. So let's combine this into one statement. Summary, LM, and the model. The data are attached this time, so we don't have to specify where they're coming from.
Why did we add homework average?
Why did we add homework average? So we're doing a multiple regression. We can put in the variables or the interactions that we're interested in. If we are interested in the variables by themselves and the interactions, then we would put the multiplication. But for right now, we want to predict test 2 from test 1 and from homework average, but not the interaction. So you should get something like this, right? And again, you see residuals. Oop, residuals up here, which is the error left over in predicting test 2 scores from both of these. Not from just one or just the other, but from both. So what's left over are errors when we have the best linear function describing the relationship between test 1, test 2, and homework average.
Can you show us the error or the Venn diagram?
The Venn diagram. Venn diagram. Okay. So I think we had T2, right?
Homework.
This is homework? And this is T1. So the residuals are coming from here. What's left over?
Is it related to partial correlation?
It is related to partial correlation. Let's talk about partial correlation maybe for a minute. In just a second, let's get down to the coefficients, because the coefficients, these are partial regression coefficients. Okay, so what do we see the coefficients? We have an intercept. Now this is different than what it was before. Why? Before it's like 17.4?
Because we add now homework average?
Yeah, we have now another variable. So when we find the slopes for both of those things, the intercept could be different. In fact, almost all the time it will be different, right? Okay, so this is the intercept, and these are our partial regression coefficients. So these are the slopes that we have. So for each increase in test 1 scores, there's an associated increase in test 2 scores of 0.47. For each increase in homework average scores of 1, there's, on average, an increase in test 2 scores of 0.23. And we see the associated t-values and also the p-values. And here we find that both of these are significant beyond a 0.05 traditional alpha level. Okay. So let's talk about the Venn diagram. So I want to make a few of them. T2, homework, T1. So this T1, this partial regression coefficient, is trying to predict T2 from T1. Now this is a partial regression coefficient. It's not a semi-partial regression coefficient. It's a partial regression coefficient. Which means that we have done what? We have got rid of, basically we have controlled for homework. It's as if we set homework to be constant. We're not allowing this to vary. So we're going to get rid of all of the variance in both test 2 and test 1 that's related to homework. Now this is different from the semi-partial. With the semi-partial, we were getting rid of only the... let's do the partial first. All right? So we find this as it's related to what's left over, what part of the T2 hasn't been explained. When we were doing the semi-partial, what we did is we ended up getting rid of the variance only in T1 that was associated with our homework average. So that would be like this. So T1, now we've taken that part of T1 out of here. Or we've taken the part of T1 that's related to homework average. And when we end up comparing, we are comparing this to all of this, as opposed to just part of that, right? So with the semi-partial, we are comparing the same thing here. These are the same. But these are not the same, right? For the semi-partial, we only semi-control for the variance of homework. For the full partial, we fully control for it. Okay, so this is the slope based on that, right? So this, T2, homework, T1. Now what we're doing, this is again a partial regression coefficient, not a semi-partial. So what we have done is we have taken away all of the variation that has been explained by T1. We're controlling for that. So now we are comparing this to that piece. So these partial regression coefficients are related to the partial correlations. So this is the error for that. This is the error for this. And we set up here, those are the residuals for basically the everything that hasn't been accounted for by T1 and T2. or by T1 and homework average.
So the residuals for both should be less than for partials.
I'm sorry, did you say that?
Residuals for both
Okay.
should be less than the residuals for partials relation.
Well, so if these are the residuals for this, and these are the residuals for that, notice that these both have the same shape, right? All right. Oh, right, degrees of freedom. So this will give us the degrees of freedom for us, which is nice and handy. Down here it says 2 and 40. So it's like 2 for the effect, 2 for the linear relationship, and 40 for the error. So how did you figure this out? Before it wasn't 2 and 40, it was something else. 1 and 41. 1 and 41. And we went to 2 and 40. What's going on? What if we added another variable? What would it be? It would be 3 and 39. Okay, so we know how to do the total degrees of freedom, right? Here we're going to find n minus 1, where n is the number of pairs or sets, right? We have test 2 scores with a paired test 1 score and with a paired homework average. It's like a set. There's a set of data for each test 2 score that we have, okay? So if you think back to that stir data, or stir my df, or stir new df, whatever it was that we were dealing with, it said we had 43 observations of 3 variables. That 43 is what we're talking about. All right, so we have n minus 1, 43 minus 1, that's 42. So those are our total degrees of freedom. Now, how do we break our total degrees of freedom up into error and effect? Well, how many things are we estimating?
1.
For what?
2. 3 is estimating 1 of 2. 1 dependent, 2.
Are you talking about the simple linear regression that we did earlier, or are you talking about the multiple regression that we just did?
Multiple is 2.
For the multiple regression, it's 2. It's not 1, it's 2. What are we estimating?
Homework.
Actually, we're not estimating 2, we're actually estimating 3. Not a line or 2, but 3. And we'll have 2 degrees of freedom. Because we're estimating 3 things. 2 slopes, 1 intercept, right? We have 3 things that we're estimating. So we'll have 2 degrees of freedom for those 3 things that we're estimating. In fact, when we figured out the intercept, we knew what the intercept was once we had the slopes. Right? All right, so once we know 2 of those, we can solve for the other. If we were estimating another slope, we'd need to know all 3 of them in order to estimate the other one. So we have 2 degrees of freedom for the linear relationship between test 2, test 1, and homework. How many degrees of freedom are left? Well, we started with 42. We used up 2 for the linear relationship. So now we have 40 left over, right? So 40 minus 2 is 40. 40 degrees of freedom for the error, yes?
If we estimate 3 or 4 slopes, how many intercepts that we will have? If only one.
How many intercepts? If we had 5
Only 1?
independent variables, yes, we will still just have 1 intercept.
Because we'll add all the more.
Because we will subtract the mean of each independent variable times its slope from the mean of the dependent variable, right? Remember when we were doing that? So we had something like mean y minus slope times mean x. And if we had multiple x's, we could say mean x1, so slope 1 minus slope to mean x2, and so on and so forth. Okay, so something that's cool. If the slopes are statistically significant, we can figure out whether the slopes are statistically significant by saying summary LM, here's the model that we have. That tells us what the slopes are. It tells us if they're significant if we have our alpha level determined, right? Now, if those partial regression coefficients are significant, the partial correlations that they are based on will be just as significant. You'll have the same p-value. Similarly, the semi-partial correlations that they are related to are also going to be significant. So if you find the significant regression coefficient, you know that this partial correlation coefficient and the semi-partial correlation coefficients are significant. So you really only need to know how to do one, and LM does that for us. Yay! We might discuss how to count the partial and semi-partial correlations for more than 2 independent variables. Remember our function, we had some correlation and then we were subtracting things from it and dividing some things. Well, those things that we subtract are going to depend on how many other variables that we're accounting for. And the same thing with the denominator. I'm not sure if we're going to cover this. We may not. Something really cool. LM knows how to handle more than 2 variables. So even though you might not know how to calculate the partials and the semi-partials or the partial regression coefficient that's based on the partial correlation coefficient, LM knows how to get it for you. How? You just need to specify the model. So it will give us the beta weights and the appropriate p-values, allowing us to determine whether each variable included in the model has a unique linear relationship with the dv. Whether that's the unique relationship with what's not explained by everything else, which is the, is that the semi or the partial? The unique relationship between a variable with what's left over. Yes, it's a partial, because it's the unique relationship between that, so we've partialed everything else from it. From what's left over in our dependent variable, we've partialed stuff from that too. So that's the partial. Or a unique linear relationship with the dv in total, which would be the semi-partial. All right, so do this. Summary, LM, T2 is a function of T1 times homework average instead of plus. The model depends on the research questions that you're asking. If you don't have a reason to believe that the 2 effects should interact with one another, you might not want to include that in your model. If you think that they're going to interact with one another, then you might want to include that in your model. So depending on what you are predicting about the relationships between the different variables, this is going to affect the shape of the models that you will use in practice. So when you do this, we are specifying 3 things, right? We want to get a linear relationship between test 2 and test 1 scores. We want to get, let me say the unique, I'll do it the long way. We want to get the unique linear relationship between what's left of test 2 after accounting for everything else and test 1. We want to do the same thing for homework average. We also want to do it for the interaction now. That's what this linear model is saying. We don't have to write it like this. We could say T1 plus homework average plus T1, sorry, those are 1s, colon homework average. But when we say this, it gives us all of this for us. Okay, so we should have something like this. You guys get this?
Yes.
All right, so again, you have the residuals, the stuff that's left over. Now we have 3 regression coefficients, and still just one regression constant. One intercept, 3 slopes. We have the values for these. Most of these are very close to 0. If we look at the p-values, what do we see? If we had a p, if the null hypothesis was that there are no correlations, and we had a 0.05 alpha level, what would we say? We would fail to reject, fail to reject, fail to reject. Notice, the intercept is significant, but none of the slopes are significant. Typically, it's the slopes that you are more interested in as opposed to the intercept, because it's the slopes that are telling you about the relationship that you have with the dependent and independent variables. Now I want you to notice something. Look at multiple r squared. What's multiple r squared? 0.579. When do you guys remember the multiple r squared that we had a little bit? 408? I thought it was 0.555. Or the adjusted one was 0.53, I think? Yeah. So before we had a 0.55, now we have a 0.53, but now we have something that's what? Is our new thing bigger or less than this?
Bigger.
It's bigger. Why would it be bigger?
Add interaction.
We've added the interaction, so potentially we could account for more variance in our test 2 scores. Now the interesting thing is, look at this. So down at the bottom we have this F statistic. This is the test of the coefficient of determination. So we have, remember earlier we talked about t-tests, and I said you could also do an F test. So this is the F test for the coefficient of determination. So the coefficient of determination is telling you how much variance in your dependent variable is accounted for by the best linear relation, or by the best linear function of all of the variables that you've included in your model. Now, the interesting thing is that this is what? Is this significant or not?
Significant.
This is significant. So the p-value right here. So this is significant. This tells us that there is a significant linear relationship between test 2 and the other variables. That's kind of weird. This is significant, but none of these are, right? This is the linear relationship between test 2 and this, well, the unique part. So what we have is that these variables are predicting test 2, but not in a unique way.
We add
Does that make sense? So these variables explain variance, a significant amount of variance in test 2. But because the variables themselves are correlated in a particular way, they don't explain any unique variance.
Is it explained the unique variance?
Pardon?
At the bottom, what we find is it significant? Is it unique relationship?
These are indicating the unique relationships. This is considering the relationships overall. Did that answer your question? Okay. So you may find that the variables are explaining variance, but that none of them are explaining variance uniquely. Before, we had both T1 and homework average explaining variance uniquely, right? But when we accounted for this other thing, that got rid of it. So imagine that we had, and this is sort of difficult because really I should be drawing this in 3-dimensional space, but I can't, so bear with me. So we have test 2, we have homework, we have test 1, and each of these sort of by themselves, we're accounting for a lot of what's left over, right? But now we threw in something else. We threw in This is our test 1 by homework interaction. And now, like, this only accounts for a little bit of the variance by itself, and this counts for less variance by itself, and this accounts for less variance by itself. If we want to think about it a little differently, imagine that we were just predicting T2 from homework. So this is, or from test 1. So we had T2 and we had test 1 earlier. And we said that that accounted for a significant amount of variance. What if we included test 1 twice? So go ahead and why don't you create a new variable? Call it T3. Say T3 equals T1. And then do summary LM T2 as a function of T1 plus, just do plus T3. Now T1 and T3 are perfectly correlated, right? Because T1, really it is T3. So if this is our T1, if we were to draw T2 over it, it's exactly over the same thing. So if we accounted for test 3, we have accounted for everything. There is nothing left unique, right? So when we included that interaction term, basically we were left with really tiny slivers that weren't significant. They didn't account for any unique variance in what was left over. So if you did this, I have not done this, but what I'm guessing is that you will have a significant R squared. But your T1 and T3 should not be significant.
There is no value for T3. It says NA.
Because they're perfectly correlated, so that's probably why. If you do, we can stop here. Anyway, it shouldn't. It should be nothing. There should be no relationship, because if you partial the same thing from itself, there's nothing else left. So this is a quirk of R. Questions? All right. Next lab, I'm not sure what we're going to do yet. We're either going to do more multiple regression correlation, we might do some other types of correlation, like experimental correlation, or maybe we'll start in our non-parametric tests. We shall see.